Okay, so how do we solve a problem like this? Well, first let's think about how to find delta G. We have an equation for delta G. We know that delta G equals delta H minus T delta S. So we need to find these three things. We'll start with the easiest. T is sort of given. It says at the starting temperature, which is 25 Celsius, which is 298 Kelvin. So that one was easy. The second easiest is delta S. We know it's one of two values. We just need the sign. So think about how to find the sign. When the reaction occurs, we're told the balloon shrinks significantly. So if it shrinks significantly, that means that fewer moles of gas are present. And how do we know that's true? Well, the external pressure is staying the same. It's, the room isn't changing because of it. The balloon's contents are heating up, so if anything, it should be expanding, but instead it shrinks. And the only real way to account for that, if we look at PV equals nRT, right? The balloon's mostly filled with gas. Temperature is going up, which would normally cause an increase in volume. R staying constant is a constant. Pressure is staying constant. The volume is shrinking. So therefore, the N, or the number of moles of gas, must be shrinking. And if there's a lower number of moles of gas after the reaction runs, that means that delta S is negative. And so it's negative 117 joules per mole Kelvin. Okay, delta H is a bit harder. We need to find a number here. But we're given all this information about mass and specific heat, and we're told that it heats up by this much. So how much is that? It's 230 degrees. You can do the math yourself, but it's 230 degrees Celsius it heats up. So that's our delta T. And what equation do we want to use here? Well, we want to use Q equals mc delta T, which is 100 grams times 5 joules per gram Kelvin times a change in temperature of 230 Kelvin, which is 115,000 joules. Okay, so we have our heating, which is our total energy that it released. So to get our enthalpy, or delta H, we need two things. First of all, we need to divide it by the number of moles of reaction. We're given that it's 0.5. So the second thing we need to do is notice that this is energy released. So we're going to have a negative value. And this is going to be equal to negative 230,000 joules per mole. Okay, so let's plug that in here. Negative 230,000 joules per mole. Now we have all the numbers. This is just a calculation. You can plug it in yourself. The answer you get is that it's about negative 195 kilojoules per mole is delta G, meaning that this reaction is pretty significantly thermodynamically favorable.